One possible solution is to say, well, since you don't point to any other nodes, I will assume that you point to all nodes. I will force you through a mandatory score spreading. You have to spread your importance score, and since you don't tell me which ones you point to, I'm going to say you point to all nodes. Okay? Either all the n-1 nodes, or for simplicity, let's say all the n nodes, including yourself with a self loop. For example, in the last graph here, instead of this 0, 0, 0, 0, we'll say it must be 1/4, 1/4, 1/4, 1/4. Now here's a shorthand notation to denote this action of forced importance score spreading to all the nodes. What we saw is that we basically say that there is 1/4 times 1, 1, 1, 1. Okay, this is a vector of ones, so we write it as a boldface 1, a vector 1. Since by convention of this research field, I have to flip it over, so this is a row vector. Okay, so it's 1/n, that's 1/4 here, times a row vector of all the ones. Okay, that's what we want to use, but only for the dangling nodes. So how we have to identify the dangling nodes? In this case, the dangling node with a binary indicator is the last one, it's the 4th node. So we write down 1 here in a 4×1 vector. It's the indicator of all the dangling nodes. If nodes 1, 2, and 3 are not dangling nodes, we just write down 0. If it is dangling node, we write down 1. And now we can look at an outer product between this column vector and this row vector. Okay, usually when we write down two vectors multiplying A transpose B, we mean inner product. Okay, so this column vector flipped, therefore it's 1/n, and B is n/1 column vector, so the inner product is a scalar, 1/1. But in this case, we're talking about a column vector producting with a row vector, not the other way around. So we actually end up with a 4×4 matrix. It's a little funny operation, but soon you'll get used to this shorthand notation. In this 4×4 matrix, the first entry is simply this times this. So that 0 times 1 was still 0. And then you can see that this whole thing would be 0. Similarly, the second row is all 0. Third row all 0. That's because in this outer product, the indicator vector's first 3 entries are all 0, so it doesn't matter what you have over there. The last one is 1 times 1/4, 1 times 1/4, and so on. So you've got exactly what you want. Again, this is just a shorthand matrix notation. And we call this indicator function vector W. This vector is just 1. So we have W multiply 1 transpose, and don't forget to normalize by the number of web pages, 1/n. In other words, we're adding to the H matrix another matrix, 1/n scalar times W indicator function and 1 transpose. Okay, just to add an arrow to indicate these are vectors. This is the matrix we just talked about. It represents the topology. This is an artificially added matrix. We add to this H. What this addition does is exactly take out all 0 rows and substitute with 1/n over there. Again, the notation may take a little getting used to, but once that's done, you can easily see what's going on here. Now H is a very big matrix, and this is also a very big matrix, but this actually is a simple matrix. Forget about the scaling. This is basically saying I'm just putting down a bunch of 1s in certain rows, those rows that are indicated as dangling nodes. And this in particular is called a rank 1 matrix. So we're adding a rank 1 matrix here, which is simply a duplication of 1, 1, 1, 1, 1 vectors, to a very large but sparse matrix H. So sparsity helps, and this low rank also helps, because we can see the structures embedded in this large matrix. We call this new matrix our second matrix. Give it a symbol H hat.